September the 18th, 1944. Chobham, England. A captured German Panther tank stood silent inside the School of Tank Technology. Its steel hull, once feared across Europe, was now cold and motionless under the harsh light of the workshop lamps. The smell of oil and burned rubber hung heavy in the air. Around it, British engineers in stained coveralls moved slowly, their tools clinking against metal. Among them was Dr. Alan Whitmore, a metallurgist from Vickers Armstrong, summoned to answer a single question from the War Office. Why did Germany's most advanced tank keep dying on its own? The Panther had been designed as the successor to the Panzer IV, a machine that combined speed, armor, and firepower into what Hitler called the perfect tank. Its 75mm high-velocity gun could punch through Allied armor at more than a kilometer. Its sloped front plate could deflect almost anything the British or Americans fired at it. And yet reports from the front were contradictory, almost unbelievable. For every Panther destroyed by shellfire, 2 more had been abandoned because of mechanical failure. Gearboxes shattered. Final drive seized. Entire battalions left their tanks behind intact but immobile. Whitmore ran his hand across the cracked surface of the final drive casing. The damage wasn't from combat. It was from within. He had seen this before. A year earlier at the same facility he had dissected the transmission of a captured Tiger. Its gears had been too hard, its steel too brittle. Now the Panther seemed to share the same fate. But the Panther was supposed to be newer, lighter, better engineered. If the Tiger had died of over-design, the Panther should have learned from it. Something somewhere was fundamentally wrong. He signaled for the crane to lift the final drive assembly onto the bench. The gears inside looked almost surgical in their precision. Finely machined teeth, polished steel surfaces, perfect symmetry. Yet one of them had sheared clean through the middle as if someone had struck it with a hammer. The fractured surface glittered under the light, smooth and crystalline, without any sign of bending or deformation. It was a brittle break. The kind that happens not over time, but in an instant. Whitmore whispered to the technician beside him, "This isn't wear. It's failure." The technician frowned, "But sir, these gears are massive. How could they just snap?" Whitmore didn't answer. He was already thinking about hardness values, heat treatment curves, and the absence of nickel and molybdenum in German steel since mid-1944. He knew the signs of industrial exhaustion. Every tank Germany built after 1943 carried not just armor and weapons, but the fatigue of a nation running out of resources, time, and skilled labor. He turned toward the team. "We'll need samples from the gear teeth and from the core. Prepare for Rockwell testing." As the men worked, the camera of an army photographer clicked in the background, documenting each step for intelligence archives. Whitmore made notes in a small leather-bound journal. Surface fracture. Brittle. No evidence of torsional fatigue. Suspect excessive surface hardness and inadequate tempering. Outside the workshop, rain began to fall. Over Chobham's fields. The sound of drops against tin roofs mixed with the rhythmic tapping of chisels. Whitmore removed his gloves and stared at the broken gear lying in his hand. To most soldiers it was just another failed machine, but to him it was a message written in steel, a story of perfection turned against itself. The Panther was meant to be the embodiment of German engineering genius. But genius under pressure he thought could turn into blindness. In their pursuit of superiority, the designers had created a masterpiece too fragile to survive its own power. Strength without resilience, hardness without toughness. The same paradox that had doomed the Tiger was repeating itself in the Panther's heart. He placed the fractured gear on the table beside a half-disassembled gearbox from a Churchill tank. Two machines from opposite sides of the war, one obsessed with complexity, the other with endurance. Whitmore scribbled one final note before closing his book. Victory belongs not to the strongest metal, but to the one that bends before it breaks. The lights dimmed. The Panther's shadow stretched across the concrete floor, a monument to brilliance undone by its own design. If you think German tanks were destroyed by Allied fire, you're not wrong. But if you believe many of them died because of what was hiding inside their own steel, you may be closer to the truth. Comment the number 7 if you agree. Like this video if you think the answer is still buried somewhere inside the gears. The next morning, the workshop at Chabam was already alive with noise. Air compressors hissed, torque wrenches clicked, and the hum of a metallurgical saw echoed across the hangar. On the center table under bright floodlights lay the Panther's disassembled final drive, the mechanical heart of Germany's most feared tank. The casing, gear clusters, and bearings were neatly arranged in rows like pieces of evidence from a crime scene. For Dr. Alan Whitmore, that's exactly what it was, a crime committed by engineering against itself. He began by inspecting the gear teeth under magnification. The damage pattern was unmistakable. Clean fractures along the root of the teeth with no trace of polishing or heat discoloration. These gears hadn't been worn out. They had been shattered by a single catastrophic load. Whitmore called over his assistant, Sergeant Miller, a young mechanical technician who had joined from Rolls-Royce's engine division. "Take a look here," he said, pointing to a broken tooth. "Notice how flat the fracture surface is. No signs of ductile tearing. It didn't bend. It snapped. That means the material was too hard." Miller nodded, his eyes wide. "But these are supposed to handle hundreds of horsepower," Whitmore replied, 700, at least on paper. But in practice, that power was eating its own gears alive. He turned to the Rockwell hardness tester, a heavy black machine with a diamond-tipped probe. Each indentation it made told the truth about a metal's life, how it had been forged, heated, cooled, and whether it had been betrayed by haste. Whitmore placed a fragment of the gear beneath the probe, adjusted the scale to the C range, and pulled the lever. The machine clicked. Then the dial needle settled at 63 HRC. Too high. Far too high. He tested again on a different tooth. 62 HRC. Another piece, 64 HRC. He wrote the numbers down slowly, as if each digit carried a weight of meaning. Transmission gears should be between 56 and 58, he murmured. Hard enough to resist wear. Soft enough to survive stress. The Germans went too far again. Miller looked over his shoulder. "You think it's the same issue as the Tiger?" Whitmore nodded, almost identical. "They harden the surface too deeply. 4 mil lime at least when it should be 2. That gives you an incredibly tough skin, but it turns the whole part into a glass shell. One shock and it explodes." He paused, letting the reality settle in. In war, tanks weren't destroyed only by enemy fire. They destroyed themselves through fatigue, heat, and stress. The British had learned this lesson the hard way with the early Crusader and Covenanter tanks, but they had improved. Germany, it seemed, had done the opposite, sacrificed durability for theoretical strength. The team continued their analysis through the afternoon. The smell of cutting oil filled the air as Whitmore used a diamond saw to slice through the gear's cross-section. The core metal gleamed darker than the outer layer. He polished the sample, etched it with nitric acid, and slid it under the microscope. At 500x magnification, the truth appeared like a battlefield scene from orbit. The surface zone was a uniform field of martensite, brilliant, sharp-edged, and deadly brittle. Beneath it, the chorus showed a faint shadow of tempered steel, softer, more ductile. Whitmore called the others over. "Look at this," he said, tapping the microscope image projected onto the screen. Pure martensite on the surface. No tempered structure, no retained austenite. It was quenched too. Fast and never tempered properly. A murmur went through the room. To the untrained eye, it was just a metal pattern. But to these men, it was a confession, a machine telling them how it had died. Whitmore began piecing together the bigger picture. Germany's industrial records captured from factories in Kassel and Nuremberg had already hinted at the cause. By mid-1944, the Reich's supply of alloying elements had collapsed. Molybdenum was gone, nickel nearly exhausted, and chromium reserved for aircraft. The steel for Panther gears had been produced with emergency substitutes vanadium and manganese, good for strength, terrible for fatigue. Worse, the heat treatment plants were being operated by semi-trained labor under constant Allied bombing. He read aloud from a report found among captured documents: case hardening procedure shortened to meet production targets, tempering step omitted when furnace capacity limited. Whitmore closed the file and sighed. They skipped tempering to save time. Every one of these gears was a time bomb. He reached for the fractured gear again. The edges were razor sharp, glinting like obsidian. "You can almost hear it," he said quietly. A tank accelerating, gears screaming, torque building, and then one clean snap. The Panther stops moving. The crew thinks they've been hit, but no shot was fired. Outside, the afternoon sun broke through the clouds, casting narrow beams through the workshop windows. Dust floated in the air like tiny embers. For a moment, Whitmore just stood there, lost in thought. The engineers who had designed this machine weren't fools. They knew metallurgy. Many of them were his peers. Before the war, some had studied in the same conferences, read the same journals. He wondered if one of them, somewhere in Germany, had written a report like his and watched it be ignored. He placed the broken piece on the bench beside the hardness data and the microstructure photograph. "This isn't just a design flaw," he said finally. "It's the symptom of an exhausted system. Too much ambition, not enough precision." The Panther, the supposed pinnacle of German engineering, had betrayed itself not through weakness, but through excess. Perfection had become its poison. As Whitmore left the workshop that evening, he looked back at the disassembled gearbox under the fading light. To anyone else, it was just another pile of broken metal. To him, it was evidence of how even the finest machines can fail when pride outruns patience. If you believe the Panther was defeated by Allied firepower, you're not entirely wrong. But if you think it was also undone by its own brilliance pushed too far, comment the number 7 below. Like this video if you believe perfection can sometimes be fatal. 3 days later, the laboratory at Chabam had been transformed into something resembling a crime scene investigation unit. Every surface was covered with steel fragments, hardness charts, and photographic negatives of microruptures. Overhead lamps glowed dim amber through the chemical haze of etching acids. In the corner, a microscope projected ghostly black and white images of Panther gear samples onto a canvas screen. The room smelled of oil metal and quiet obsession. Dr. Alan Whitmore leaned forward, studying a magnified cross-section of a gear tooth. Under 500x magnification, the steel looked like a frozen storm, needles of martensite stretching across the surface. Like shattered glass. The deeper layers were calmer, softer, filled with faint gray streaks of tempered ferrite. He pointed to the screen, his voice steady, but grim. This is what killed them. No tempering, no ductility, no forgiveness. His assistant, Sergeant Miller, took notes quickly. What exactly are we seeing here, sir? Martensite. Whitmore replied, it's what you get when steel is cooled too fast. It's hard, harder than anything else in metallurgy, but it's brittle. It has no flexibility. Under shock, it doesn't bend, it breaks. And that, he said, tapping the screen, is what every one of these gears was made of. Miller frowned. They should have tempered it, then heated it again just below critical temperature. Exactly. Tempering relieves stress. It turns some of that martensite into tempered martensite, a structure strong yet elastic. But these, he gestured toward the samples, were never tempered properly. Maybe not at all. Whitmore opened a folder stamped "Captured German Industrial Documents, 1944. Inside were brittle pages filled with typed German text and hand-drawn charts. He flipped to a section labeled Werkstoff 39 Men RM5, the Panther's gear steel. Before 1943, this alloy contained molybdenum and nickel, two elements that make steel tough. By 1944, both were missing, replaced by vanadium and manganese. The result: steel that's strong at first but can't survive sudden stress. He read a translation aloud. Heat treatment procedure: carbise for 14 hours. Quench an oil temper at 200 degrees Celsius. For 1 hour. Whitmore's brow furrowed. 1 hour. That's half of what's needed. At 200 degrees, that's barely a temper. The steel remained too hard. That's why we're seeing surface hardness readings of 63 Rockwell C. Miller asked, why would they shorten the tempering time? Whitmore turned away from the microscope and sighed. Because they had no choice. Every furnace in Germany was overloaded. Skilled workers were gone, drafted dead. Or replaced by forced laborers who didn't understand metallurgy. Bombing raids cut power, destroyed plants, so they cut time. Carbized quench ship. The tempering step was treated as optional. He walked over to the furnace. Data sheet pinned to the wall. Look at this case: depth 4 mm, too deep. The gear's outer shell became a thick glass layer around a soft core. The moment torque hit the stresses focused at that brittle boundary. The gear exploded from the inside out. He paused, then added quietly, it's not bad engineering. It's desperation disguised as perfection. The British team expanded their testing, cutting additional samples from the Panther's gearbox and comparing them to earlier Tiger transmissions. The results were almost identical. Excessive hardness, high carbon gradient, and poor tempering. The pattern was systemic, not isolated. Whitmore documented each measurement in his report. Surface hardness 6264 HRC, core hardness 52 HRC. Case 3.84. 84.2 fracture mode brittle intergranular 0. Plastic deformation. He dictated his conclusions into a field recorder. All failed gears show identical. Microruptural characteristics predominantly untempered martensitic. The mechanical consequences. Catastrophic failure under shock loads, particularly during sudden direction changes or acceleration. The Panther's final drive, as designed, is incapable of surviving its own inander torque. Output. The room fell silent for a moment. The sound of distant rain returned tapping against the windows. Whitmore placed his hands on the bench and whispered. They built machines too powerful for the materials they had. Left. That night, while the rest of the staff had gone home, Whitmore stayed behind, staring at the fractured samples. Laid out under the microscope light. He couldn't stop thinking about his German counterparts, the engineers at Mannheim and Daimler-Benz, men who had once been his colleagues in pre-war conferences. They must have known, he thought. They must have seen the same fractures, the same failures. But their world no longer allowed for slow fixes or perfect procedures. He opened a letter from the British intelligence liaison summarizing intercepted German factory communications. One passage stood out. Production of Panther gear components delayed by furnace failure directed from Berlin reduced process time by half to meet quota. Whitmore sat back in his chair, running a hand through his hair. They destroyed their own reliability. Chasing numbers. He began writing his section of the final report. Each paragraph felt like a eulogy for science. Under tyranny. The final drive design of the Panther is elegant, he wrote, but fatally sensitive. It relies on precise metallurgy that Germany's collapsing industry can no longer sustain. The result is mechanical brilliance undermined by chemical starvation. The next morning, they performed a stress simulation test on one of the recovered gear assemblies. Using an electric dynamometer, they applied progressive torque to the final drive at intervals of 100 ft-lb. At 200 foot-pounds. Well below combat conditions, the main gear failed with a sharp metallic crack. The sound echoed through the hangar, startling the technicians. Whitmore watched as oil dripped from the ruptured casing. The gear split into two neat halves. He recorded the data, then spoke softly to the team. That sound, he said, isn't defeat by the enemy. It's defeat by physics, Miller asked. So every Panther out there could break the same way. Whitmore nodded. Every single one, every tank carrying this gearbox is living on borrowed time. Outside, the gray skies of England mirrored his thoughts. The war was still raging in Europe. But Whitmore knew that for every Panther advancing toward the front, another was already doomed by its own metal. The lesson was as old as engineering itself. Strength without resilience is failure. Waiting for a trigger. He packed the fractured sample into a wooden box labeled evidence of final drive. Panther. G. On the lid, he wrote in pencil, destroyed not by fire or shell, but by the absence of temper. If you believe that battles are won by courage alone, you're mistaken. Sometimes they are decided by carbon percentages and the color of heat in a furnace. Comment the number 7 if you agree. Like this video if you believe that every failure tells a story written in steel. August 1944. The fields of Normandy were burning along the narrow French roads. A column of German Panther tanks moved cautiously through the smoke. Engines roared, gears shrieked, and the smell of hot oil and exhaust hung heavy in the air. These machines, sleek, angular, and deadly, were supposed to be the answer to Allied armor. Yet, even before they reached the battlefield, half of them were already limping. Inside, one of the Panthers, Lieutenant Hans Kruger, shouted over the noise of grinding metal, "Something's wrong with the drive." His driver wrestled with the controls, but the tank shuddered violently and slowed to a crawl. A moment later, there was a sharp crack followed by a jolt that threw the crew against the steel interior. The right track locked completely. The tank stopped. Outside, other Panthers swerved to avoid the sudden obstacle, but one after another began to fail the same way. Final drive seized, gears snapped, oil burst into flames. Within minutes, a third of the column was immobile. To the Allied pilots flying overhead, it looked like victory. Rockets from Typhoon stray down, striking the stranded tanks. But the real destruction had already happened inside the gearboxes long before the attack began. Back in Berlin, engineers were struggling to explain the crisis. Field reports described mechanical breakdowns at unprecedented rates. The official summary from Panzer Regiment 26 read 43% of all Panthers unserviceable after less than 150 kilometers of operation. Principal cause: final drive failure. The report landed on the desk of General Heinz Guderian, Inspector of Armored Troops. He was furious. "This is sabotage," he snapped. "No machine fails like this by accident." But sabotage was not the cause. Metallurgy was. At the same time, captured Allied intelligence reports confirmed what Dr. Whitmore had already written in his notebooks at Chobham. The gears were too hard, too brittle, and too deeply case-hardened. Every turn of the steering lever sent shock loads through the transmission that the steel simply couldn't absorb. Under stress, the gears shattered cleanly. No warning, no noise, just one instant of silence, followed by immobilization. German maintenance crews called it the curse of the Panther. They could fix engines, replace tracks, even patch armor, but not final drives. Once they failed, the tank was finished. Replacement parts were scarce, and the few that arrived from the factories were often just as defective as the originals. In the field workshops of Normandy, mechanics worked through the night under tarps lit by kerosene lamps. They opened the gearboxes and found glittering fragments of steel swimming in oil. Every tooth on the main gears had small radial cracks starting from the root. Microscopic flaws that spread until the entire wheel collapsed. One mechanic reportedly muttered, "You can hear them crying before they die." By September, the pattern was undeniable. A captured German technical report from the Man factory read, "Under combat conditions, Panther final drive failure. Rate exceeds acceptable limits, cause suspected insufficient case hardening. Control improper heat treatment due to production urgency." Even in Germany, engineers were beginning to admit the truth. But it was too late. Hitler, obsessed with heavier armor and larger guns, refused to reduce the tank's weight or simplify its design. When reports reached his headquarters that gearboxes were failing under stress, his only order was to reinforce them. The result was predictable. Each modification made the components heavier, increasing the torque load, accelerating the very failures it was meant to prevent. By late 1944, Panther divisions on both fronts were crippled by their own complexity. In the Ardennes, Panther tanks deployed for the winter offensive struggled to move through snow and mud. Dozens broke down before reaching the front lines. American reconnaissance units later found them abandoned in perfect condition, their Engines intact, but their final drives frozen solid. Allied analysts documented the phenomenon meticulously. One British report filed under Panther reliability assessment concluded mechanical reliability remains critical vulnerability. Enemy tank crews frequently destroy vehicles themselves after transmission seizure. Tactical mobility compromised to the point of strategic irrelevance. In the intelligence archives, Whitmore's findings had been marked validated. His earlier predictions that brittle gears would fail under combat stress were confirmed by the battlefield. It was one of those rare moments when a scientist's hypothesis translated directly into military reality. Meanwhile, inside Germany, engineers tried to fix the problem by experimenting with different steels and heat treatments. But every attempt faced the same constraints. Shortages of alloying elements furnace. Damage from air raids and inexperienced workers. Quality control inspections were often skipped entirely. Factories received orders from Berlin that emphasized numbers over durability. More Panthers faster at any cost. A report from a captured Panther unit near Ain summed it up with grim honesty. We can destroy enemy tanks easily, but we cannot reach them. The final drive kills us before the enemy does. On a cold December morning, one Panther commander wrote in his logbook, "Our tanks are lions with broken legs. They look powerful. They roar, but they cannot run." That sentence found among captured documents after the war became a haunting metaphor for German engineering. In its final phase, magnificent in theory, crippled in execution. In March 1945, as Allied forces crossed the Rhine, entire Panther battalions were abandoned without a fight. The cause was always the same: seized transmissions, fractured gears, and final drives that failed just as tanks tried to turn or climb. Soldiers set demolition charges and walked away, leaving the burned-out shells behind. The myth of invincibility died quietly. Not in battle, but in a cloud of oil smoke and broken steel. When British intelligence compiled the post-mortem reports, Whitmore's name appeared again in the technical appendix. His 1944 analysis had predicted everything: the brittle Martin sight, the skip tempering the excessive case depth. What had been theory in a laboratory was now written across the battlefields of Europe in hundreds of immobilized tanks. If you still think the Panther was defeated by enemy guns, think again. It was defeated by its own engineering, a masterpiece designed for perfection, destroyed by haste. Comment the number 7 if you agree. I'll like this video if you believe that no weapon, however powerful, can survive when science is sacrificed for speed. October 1944. The rain had turned the French countryside into a swamp of mud and broken machinery. Allied commanders were studying the same question that haunted German engineers. Why were so many Panther tanks being found abandoned, intact without a single shell hole? The answer came quietly through a report marked Confidential School of Tank Technology. The author's name at the top was already familiar to a few officers. In British intelligence, Dr. Alan Whitmore. His findings were brief but devastating. Panther final drives exhibit brittle fracture under torsional shock loads exceeding 3,000 foot PBS. Failure occurs during sharp turning, rapid acceleration, or sudden braking. Recommend tactical exploitation through forced maneuver. In simpler words, if the Panther could be made to turn sharply or reverse direction under combat pressure, its gears would fail without the Allies firing a shot. Major General Percy Hobart, commander of Britain's 79th Armored Division, understood the implications immediately. He had already built a reputation for transforming engineering theory into battlefield advantage. Churchill bridge layers, flail tanks, amphibious Shermans. Now he saw another opportunity. He circulated Whitmore's report to armor battalion commanders with a handwritten note. The Panther's strength is its weakness. Force it to move. Do not fear it. Make it dance and it will die. Training manuals began to include subtle tactical adjustments. When encountering German armor, Allied crews were instructed not to engage the Panther head-on, but to provoke movement. Attacking from multiple angles, forcing the tank to pivot rapidly on its tracks. The greater the torque on the final drive, the higher the chance of mechanical failure. In late October, during skirmishes near Ain, British Cromwell tanks used this exact approach. Reports described a Panther platoon caught while repositioning to face flanking fire. Two of the tanks turned sharply on wet ground. Both stopped abruptly. Engines still running, tracks jammed. The crews, believing they had been hit, bailed out under fire. Allied forces captured both vehicles intact. Technical inspection confirmed the cause: shattered drive gears. No projectile damage. Whitmore received a field telegram that simply read, "Your report confirmed. Panther immobilized by turning stress. Hobart sends regards." He folded it carefully and placed it inside his notebook beside a fragment of the gear he had studied months earlier. As 1945 approached, Allied commanders refined the tactic further. Intelligence briefings described the Panther's vulnerability in precise mechanical language. The double-spur final drive system, compact but overstressed, created lateral thrust loads during aggressive steering that exceeded the brittle steel's yield strength. The solution was not more firepower, but patience and precision. Let the German tank move first. Let it destroy itself. On the snowy hills of the Ardennes, American Sherman crews applied the lesson instinctively. When Panthers appeared on the horizon, they spread out and fired smoke shells rather than armor-piercing rounds, obscuring vision and forcing the heavier tanks to turn repeatedly to search for targets. In one after-action report from January 1945, the U.S. platoon leader described what followed. "We kept them turning. Within minutes, 3 Panthers stopped moving. No hits observed. Engines running, smoke from the rear decks, transmissions likely seized. They blew their own tanks and withdrew." Back in England, Whitmore's technical notes became part of an official field guide circulated by the British War Office. Enemy Panther tank mechanical vulnerability, final drive overload under torsional shock, recommended countermeasure: exploit through forced maneuver. To most soldiers, it was a simple footnote. To Whitmore, it was proof that science could shape the outcome of war without a single shell being fired. He was summoned once more to London, this time to brief a group of officers from Allied Armored Command, standing before them with projected slides of metallurgical micrographs behind him. Whitmore explained the invisible battlefield inside every machine. "Gentlemen," he said, "a tank is not destroyed only by what strikes it. It can also be defeated by what it carries within. The Panther's transmission is its Achilles heel. Force it to act beyond its design, and physics will do the rest." One officer asked, "You mean we can make them break themselves?" Whitmore nodded. "Every mechanical system has limits. Theirs are visible now. Turn radius, gear, stress, temperature rise. Numbers don't lie. You don't fight the Panther, you let it fight itself." By February 1945, Allied tank commanders had fully integrated the concept into operational tactics. During the crossing of the Roer River, British armor units deliberately maneuvered across uneven ground, forcing nearby German tanks to react quickly and strain their transmissions. Out of 9 Panthers engaged, 4 suffered mechanical breakdowns before any direct hits. The intelligence summaries that followed were blunt. Enemy heavy tanks remained tactically vulnerable due to mechanical fragility. Recommended maintain mobility pressure, avoid static engagements. For Whitmore, it was a strange kind of victory. His research, born in quiet laboratories, among steel fragments and microscopes, now shaped real combat decisions across Europe. The gears that had once betrayed the German war machine were now betraying it again, this time strategically, but the satisfaction was tempered by unease. Whitmore understood that his discovery didn't just expose mechanical weakness. It exposed the human one, the arrogance of believing that perfection could be rushed, that brilliance could replace patience. He wrote in his diary that evening, "In war, the engineer fights not against the enemy, but against time. Time wins." By March, as Allied forces reached the Rhine, Panther wrecks lined the roads in dozens, many untouched by shellfire. Intelligence officers inspected them, finding the same signature every time fractured gears seized transmissions. Metal glittering like broken glass. To them, it was confirmation. To Whitmore, it was tragedy. Each failure was the echo of an engineer's compromise. A furnace cooled too fast, a tempering cycle skipped to save hours. History would record the Panther as one of the most feared tanks of the war. But in the classified annexes of Allied reports, another description appeared beside its name: operationally unreliable due to final drive failures caused by improper metallurgical treatment. Whitmore's work had begun as analysis. It ended as strategy. If you believe that wars are won only with bullets and bombs, think again. Sometimes they are won with observation, patience, and the quiet precision of engineers. Comment the number 7 if you agree. Like this video if you believe knowledge can be more powerful than firepower. May 1945. The war in Europe was over. The sound of artillery had faded into silence, leaving behind only the mechanical ghosts of a conflict built on steel. Across the continent, tanks lay abandoned in fields and villages. Some burned out, others simply stopped in place, their engines cold and gears frozen in mid-turn. Among them were hundreds of Panthers, their imposing silhouettes now monuments to a paradox. Engineering brilliance undone by its own ambition. In London, Dr. Alan Whitmore stood in the archives of the War Office staring at a final report stamped declassified transmission failure. Panther series. It summarized 2 years of work in a single unemotional sentence: catastrophic final drive. Failures attributed to excessive surface hardness and inadequate tempering. 2. The bureaucrats, it was a closed case. To Whitmore, it was the most important lesson of his career. The British government offered him a position on the post-war tank design board. Britain was already looking ahead to a new generation of armored vehicles that would have to balance firepower, mobility, and reliability in a world that no longer had the luxury of haste. Whitmore accepted not for prestige, but for the chance to ensure that what had happened inside the Panther's gears would never happen again. At the first meeting of the board in early 1946, Whitmore spoke before a room of engineers and officers. On the table lay a fragment of fractured German steel, the same gear piece he had carried since Chobham. Gentlemen, he began, this is not the story of German failure. It is the story of what happens when precision is sacrificed to production, when knowledge is forced to obey orders. The Panther was not poorly designed. It was rushed beyond the limits of its materials. He proposed new standards for British tank metallurgy, precise limits for hardness, case depth, and alloy composition. No gear, he declared, shall exceed 58 Rockwell C at the surface. Case depth shall be no greater than 2.5 millimeters. Tempering cycles will be verified for every batch before assembly. The specifications were adopted in full and became the foundation for the post-war Centurion and Chieftain tank programs. Over the next decade, these new machines earned reputations for reliability that their German predecessors had never achieved. Their transmissions were overbuilt. Their steels thoroughly tested, their quality control relentless. Engineers called it Whitmore's Law. A simple rule written in the margin of early design drafts. Strength means nothing without resilience. In the 1950s, Whitmore returned to academia, accepting a position as a lecturer in material science at Imperial College London. His students never knew the full extent of his wartime work. The documents remained classified and Whitmore rarely spoke of it. But occasionally during lectures on heat treatment and phase diagrams, he would hold up a small steel fragment and say, "This piece of metal changed how nations build machines." It reminds us that the line between power and failure is thinner than a human hair. In quiet moments he thought about the German engineers he had once read about, men who like him had studied the structure of steel, who had understood the beauty of precision but had been crushed by the machinery of war. He didn't hate them, in some way he pied them. They had been forced to build weapons instead of understanding them. They had turned science into urgency and urgency into fragility. In 1962, when Whitmore visited the Tank Museum in Bovington, he finally saw a restored Panther on display. It was painted in the colors of the Wehrmacht. Its hull immaculate, its turret polished, but Whitmore's eyes went straight to the lower hull, to the final drive housings. He knew what was inside, even if no one else did. The steel was still the same, hard, brittle, unforgiving. He placed his hand on the cold armor and whispered, "You were brilliant and broken." Years later, his students found that fragment of Panther gear in his office drawer, labeled in careful handwriting, Panther Oasis F. G. Chobham, 1944. Evidence of overhardening. They donated it to the museum after his death. Today, it rests beside other relics of the war: propellers, shell casings, shattered armor plates. Most visitors walk past it without noticing. But those who stop to read the small placard understand the quiet message it carries, that even the strongest metal must yield a little or it will destroy itself. The legacy of Whitmore's discovery was not just better tanks. It was a deeper understanding of how science and ethics intertwine. His students would go on to design aircraft, bridges, and machines that carried the same philosophy, designed for endurance, not perfection. In one of his final interviews before retiring, Whitmore was asked what he thought of his wartime contribution. He smiled faintly and replied, "I didn't win a battle. I only proved that truth leaves fingerprints, even in steel." If you believe that progress comes not from speed, but from understanding, comment the number 7. Like this video, if you believe knowledge outlasts war. The light in the museum dimmed as the doors closed for the evening. The last sound of fade was the slow hum of air vents moving through rows of silent machines, engines, armor plates, fragments of steel once meant to decide the fate of nations. At the far end of the hall stood the Panther tank, its paint flawless, its form as imposing as it had been in 1944. Visitors often stared at its sloped armor, its great cannon, its shape of power. Few ever looked lower where two small rounded housings sat near the tracks, the final drives, the place where perfection had broken itself. A small display case nearby held a single object, a fractured gear polished on one side, jagged on the other. The label beneath it read simply, Panther G, recovered 1944. Structural failure due to improper tempering. No grand description, no drama, just the quiet truth of a war told through metal. If you listen closely, you can almost hear the echo of that truth in every battle since. Because war, when stripped of its flags and fury, has always been an argument between knowledge and arrogance, between what we understand and what we refuse to admit. The legacy of Dr. Alan Whitmore was not written in medals or honors. It lived instead in the steel that came after him, in every transmission that endured stress without cracking, in every gear that flexed and survived where the Panthers had shattered. The engineers who learned from him carried his principles into an age that was supposed to be beyond war aircraft. Stronger yet lighter engines that ran longer, machines that respected their own limits. Whitmore once said, "A perfect design is not the one that never fails. It's the one that fails safely." It was a sentence born from years of watching perfection collapse under its own weight. And in the quiet of his later life, when asked what haunted him most, he answered, the sound of metal breaking, not because it failed, but because someone forced it to succeed too fast. Standing in front of the Panther, it is easy to be mesmerized by the beauty of its construction, by the precision of its form. But beauty in steel is deceptive. Beneath that elegance lay a flaw invisible to the naked eye. A flaw born from pressure, from desperation, from the human need to be perfect even when perfection kills. The Panther was not defeated by the enemy's weapons. It was defeated by its own process, by heat treatment shortcuts, by skipped tempering, by decisions made under the weight of war. Each fractured gear was a confession. Each seized transmission, a verdict that ambition without restraint is just another form of failure. After the war, Whitmore's reports were filed away, the data absorbed into design standards, the names of his assistants forgotten. Yet, every modern tank, every armored vehicle that works as intended, carries a trace of his work, an unseen inheritance of integrity. The lessons of the Panther's broken gears live on not as warnings but as commitments. That no steel should be hardened beyond its ability to endure. That no engineer should be rushed beyond reason. And that truth in metallurgy is truth in life. Resilience matters more than strength. When historians talk about the Panther, they speak of its gun, its armor, its silhouette on the battlefield. But the real story lies in its silence. The moment when its gears stopped turning. When the world's most advanced tank became a monument to what happens when science serves speed instead of understanding. Whitmore's gear fragment now sits behind glass, a single piece of steel that outlasted empires. Generations of engineers passed by it without realizing that this small broken part once changed how nations think about reliability, ethics, and endurance. It is not a symbol of defeat. It is a symbol of honesty. So as you leave this story, remember that progress is not built on victories. It's built on what we learn from what fails. The same heat that hardens steel can also destroy it if handled without care. the same brilliance that builds great machines, can also break them when it forgets humility. War will always test machines, but in the end, it is knowledge that decides which ones survive. If you've stayed this far, you are not a casual viewer. You're someone who understands that history is not just names and dates. It's chemistry, pressure, and choice. Comment the number 7 if you believe that real strength lies in resilience, not perfection. Like this video if you believe that science, when done with integrity, saves more lives than it ever takes. And if you want to keep learning how engineering shaped the outcome of the 20th century, how gears, alloys, and unseen equations decided who won and who lost, subscribe now. Join a community that values depth over drama, precision over noise. This is War Tech Archives, where we don't just tell you what happened, we show you why it happened. Where steel speaks and history listens. Subscribe, click the bell, and stay with us. Because the story of steel isn't over, it never ends. It only waits for someone to look close enough to see the truth written in its grain.